Exercise 47. Let's further generalize that exercise 44, 45. So actually it's about this orthogonal transformation on Rn, which means those transformation preserves dot product. Recall that for dot preserved inner product in some sense, right? And particular case would be taking the inner product with dot product. That's the classical orthogonal group, ONR or ORN. That would be M, T, M equals identity, right? Those n by n square matrix with row entries. And more general, we discussed if your inner product is given by x, y inner product equals x transpose a y, then we could further describe this as MT A, M equals A. This was discussed in exercise 45. And let's further generalize this. This is very artificial, but let me say fix so let me remark this preserved dot product, this preserved the inner product, right? So in some sense it's preserved, it's angle preserving or length preserving or inner product preserving. That corresponds to the orthogonal transformation. Let's say that exercise 47, fix a positive integer and assume T from Rn to Rn is a linear transformation and assume M is the matrix of T then we want to describe, so let's say with respect to standard basis, so we want to describe this matrix M such that it is something's length preserving or angle preserving, something like that. Actually, length preserving would be stronger than angle preserving, because length preserving, once you preserve length, you preserve the angle. Because in your triangle, the length, once the lengths are settled, this angle is determined. But angle preserving does not really imply length preserving. Just imagine that you have something linear transformation that just scalar multiplication, right? It just like zoom in, zoom out. This would be something I think in some contexts called conformal maps. But we're not going to talk about this. Okay, so let me continue. With respect to standard basis, let's write this matrix M. Assume let me write this. So this is kind of confusing because when we write this, we mean inner product. But let me say this is denote just a bilinear map, which is non-degenerate symmetric bilinear form. on Rn. And that corresponds to this bilinear map. We could rhythmically similar as what we did in exercise 45, using a matrix C to express this bilinear map. So let's say C is the n by n matrix such that W equals transpose of W multiplication with Z multiplied with W. So those are matrix multiplication. Then show the following conditions. Are equivalent. Firstly, this linear transformation preserves that bilinear form, preserve the bilinear form. That is, for any V and W nor n, this bilinear is equals the bilinear of the image. Secondly, we characterize it by matrix transformation. MT say M equals say. Okay, so actually the proof of this is almost the same as what we did in exercise 45 in the sub-exercise. Basically, this was discussed in the sub-exercise of exercise 45. Okay, so basically it's the same proof. So let's say bilinear form preserving, and so let me use X and Y. That's more familiar, right? So this is transpose of X times Y as matrix transformation, and then H equals Tx Ty, which is Mx transpose My, and so this is X transpose M transpose M, and then Y. This equals wait for a while. Yeah, well, this is not dot product. Our bilinear is given by C. This is it, right? So we have this, and so this bilinear form preserving is equivalent to, hence, xt m t c m y equals xt c y for whatever x and y are n, and in particular, this is telling us that B implies C, right? If for MTCM equals C, then this is bilinear preserving, B implies A. And for A implies B, it requires, again, use test vectors. So if we take X to be EI, Y to be EJ, then this would tell us EI transpose say EJ equals EI transpose, so this matrix TCM, then EJ transpose, and then EJ. So what is this? This is, let's say 0, 0, 0, and then 1, this in the i's column, and then 0, 0, 0, and then you have this C, let's say Cij, just, and then this EJ 0, 0, 0, and then 1, this is in the J's row. And what is this? This is the left hand side. Left hand side equals this. So you see this only first row, first column, first row, second column, and you see this cut out this say I1, CI2, CIN, cut out this ith row, and then multiplication with this cut out this CIJ, right? So, which means similarly the right hand side would exactly be, if you call this matrix B, I mean, if you call this matrix with entries Bij, then this would imply the right hand side cut out Bij, and so Bij equals Cij is telling you that C equals TCM, and so this is done. So this is not really the purpose of this exercise. Actually, here the generalization is that, okay, we don't require that much on this bilinear map. We don't require it as much as for inner product. Non-degenerate is just telling you that as bilinear form, xy equals 0 for any y, imply that x equals 0, right? But this is our non-degenerate. But as inner product requires you something called positive definite, which requires that. So x xx bigger than 0 for any x, and equals 0 if and only if x equals 0. So this positive definite would imply this non-degenerate, right? Because if your inner product, if you're bilinear with all the vectors of 0, in particular with yourself at 0, so it must be 0, right? But this direction is not true, right? Because, so let's take an example. If you use your matrix C to be 1, 0, 0 minus 1, and then your, so we're talking about in R2, right? So your bilinear map induced by this would be x transpose C, y would be x1, y1 minus x2, y2. So let's check this, because this is just x1, x2, and then 1, 0, 0 minus 1, then y1, y2. What you have is, so first row, first column, first row, second column, first row, and then equals x1, y1 minus x2, y2, right? So for this one, is it positive definite? So question, x bigger than 0. So this is x1 squared minus x2 squared, right? So of course not. So this is not positive definite. But it still makes sense. Actually, this has physical meaning. This is what I call Lorentz product, right? So let me remark on this. So we denote this by Lorentz group L2R. I'm talking about in R2. So in general, this orthogonal group, you could think of it as a group of geometry of Euclidean plane. If it's the dot product, then the group of symmetry would be the classical ORN. If the inner product, then the group of symmetries you think of could be the one we described in exercise 35, sub-exercise. And if it's this Lorentz product, which is the C I described here, then the group of symmetry of this Lorentz plane R2, that is the linear transformations of R2 which preserve the Lorentz product, and hence the what is called interval in physics. This will be denoted by either this or this one. Is described similarly to be those matrix 2 by 2 matrix with real entries such that M transpose C M equals C, where C is that C described here. Okay, and we can even further to like how we classify all the matrix for OR2, right? Recall the exercise 46 should be, we classify all those matrices in R2. There are two types: rotations, reflections. Similarly, sub-exercise, you could classify all the matrix in this Lorentz group and show that there are four types. So first, two types cosine hyperbolic alpha, sin hyperbolic alpha, sin hyperbolic alpha, cosine hyperbolic alpha, or cosine hyperbolic alpha minus sin hyperbolic alpha, sin hyperbolic alpha minus cosine hyperbolic alpha. These first two types, they are rotations and reflections of the first type. Rotations and reflections of the first type. And you have second two types minus cosine hyperbolic of alpha, sin hyperbolic of alpha, and sin hyperbolic of alpha minus cosine hyperbolic of alpha, or minus cosine hyperbolic of alpha minus sin hyperbolic of alpha, sin hyperbolic of alpha, cosine hyperbolic of alpha. The corresponds to what's called rotations, reflections of the second type. And show this is a group, and then it has two subgroups of interest. So the first is L plus, the group of rotations of both kinds. So group of rotations of first type and second type. And L double plus is the group of rotation of the first type. Finally, we might give a proof of this in the following exercise. Before we do that, so usually we call this let's say T1x1, T2x2, which is T1, T2 minus x1, x2, is called the interval Lorentz product. Sorry, Lorentz product on R2.